You've got a million embeddings. Now what? In the last video you learned how to turn text, images, and audio into vectors, long lists of numbers that capture meaning. But a vector sitting in memory does nothing on its own. The real power is search. Given one vector, instantly find the handful that are closest to it, out of millions, and do it before the user even notices a delay. That single ability is the whole reason a vector database exists. And once you get how it works, a huge chunk of modern AI stops feeling like magic and starts looking like plain engineering you could build yourself. So let's build the whole thing up step by step, from the naive version that falls over to the one that actually ships. Start with the obvious approach. You have a query vector, and you want its closest match in your collection. The simplest possible idea is to compare that query against every stored vector, one at a time, and keep whichever one is nearest. And honestly, that works great when you have 1,000 items. It's exact, it's simple, nothing can go wrong. But watch what happens as your data grows. 10,000 vectors still fine. 100,000 noticeably slower. 1,000,000, and every single search now compares against 1,000,000 long lists of numbers, where each comparison is real math across hundreds of dimensions. Each of those comparisons multiplies and sums hundreds of values, so a single search can burn through well over 1 billion tiny operations. Run that on every query for every user all day long and your app grinds to a halt. The wait creeps from milliseconds to a full second to something people abandon. Checking everything simply does not scale. So here is the core idea, and it's beautifully simple. A vector database is really two things bolted together. 1, a place to store all your vectors and the data attached to them. 2, a smart index that can find the nearest vectors without ever checking them all. Storage is the boring half. Almost anything can hold a pile of numbers. The index is where the genius lives. It organizes your vectors ahead of time by where they sit on that map of meaning, so that when a search comes in, you don't scan the whole library. You jump straight to the right shelf. Store the vectors, build the index, search in milliseconds. That's the entire product in a single line. Let's name what we're actually searching for. The technical term is nearest neighbor search. Picture your query as a single new point dropped onto the map of meaning. The answer you want is just the points sitting closest to it, its nearest neighbors. Ask for the top 5, you get the 5 nearest. Ask for 10, you get 10. That count is usually just called K. You're asking the database for the K closest points, no more and no less. And remember, closeness here is that similarity score from last time. A small angle between two vectors means a high score, which means a near neighbor. So the fuzzy human question, what is most similar to this, becomes a precise geometric one. What is nearest on the map? Same idea you already understand, just with a name that shows up in every database's documentation. This is where the index changes everything. Instead of dumping your vectors into one giant unsorted pile, the database groups nearby vectors together in advance before any search ever runs. Think about a real library. With no system at all, finding one book means walking every single aisle shelf by shelf until you get lucky. Add a catalog and you walk straight to the exact shelf in seconds. The index is that catalog, except it's built for meaning instead of titles. When a query arrives, the database uses the index to leap to the right neighborhood of the map, and then only compares your query against the few vectors that could realistically be close. Everything else it never even looks at. You skip almost the entire dataset completely on purpose, and you still walk away with the right answer. That single move, organize once, jump instead of scan, is the beating heart of every vector database on the market. Zoom in on that neighborhood and ask how the index is actually built. There are a couple of popular families here. One approach slices the whole space into buckets or regions ahead of time, so a query only has to open the buckets sitting near it. The approach you'll see most often today builds a layered graph instead. Every vector gets linked to its closest neighbors, and the upper layers act like express lanes stretched across the map. A search drops in at the top, takes big hops in the rough direction of the target, then descends layer by layer to fine-tune. This graph method has a specific 4-letter name you'll spot everywhere in the docs, shown right here on screen. But the intuition is what actually matters. Follow the links and you land on the closest vectors in a few dozen steps instead of 1,000,000 exhausting comparisons. Here comes the payoff number, and it's the one to remember. Because a good index lets you skip almost everything, search stops caring how big your data gets. A well-built index can find the nearest neighbors inside a collection of 1,000,000 vectors in single-digit milliseconds. Faster than you can blink, faster than the screen can even redraw. Push it to tens of millions of vectors and it barely slows down because the work grows with the logarithm of your data, not in a straight line. Double the size of your collection, and search time ticks up by a sliver instead of doubling. In practice, a search across 10 million vectors can cost barely more than a search across 1 million. That gap between a million comparisons and a few milliseconds is the entire difference between a cute demo and something you can put in front of real users. Now here's the honest trade-off, because there is one. That layered graph search is not guaranteed to be perfect. It's called approximate nearest neighbor search for a reason. Every now and then it misses a true closest match and hands back one that's just slightly further away. In exchange, it runs hundreds of times faster than checking everything. The quality of the results is measured by something called recall. Out of the items that were truly nearest, what fraction did you actually find? If the true top 10 and your return top 10 overlap on 9, that's 90% recall. Good systems hold well over 95% recall while staying blisteringly fast, and you get a dial to turn. Spend a little more time searching for a little more accuracy, or the other way around. For search and recommendations, missing the occasional edge case is completely invisible to the user. For something like billing or legal lookups, you'd keep the exact slow method. Just pick the trade-off that fits the job. Let's look at real results from a real query. Say you run a customer support tool and a user types, "My card keeps getting declined." You embed that sentence, hand the vector to the database, and ask for the nearest neighbors among all your help articles. Back comes a ranked list, and each result carries a similarity score. Payment method was rejected, 0.91. Update your card on file, 0.83. Shipping and returns, 0.31. Notice the top hits share almost no actual words with the query, yet they're obviously the right answers, ranked cleanly by meaning. That score is the whole reason this feels like search that finally understands what you meant, instead of just matching the letters you typed. And because every answer arrives with a number attached, you can set a floor. Anything scoring below, say, 0.5, you quietly drop as not relevant enough to show. Real apps need one more thing on top of raw similarity, and it's easy to overlook. Pure nearest neighbor search will happily hand you the single most similar item that happens to be out of stock, or from the wrong user, or written 3 years ago. So every serious vector database lets you attach plain metadata to each vector: a price, a category, an owner, a date, and filter on it during the search itself. Now the query becomes, find me things similar to this and in stock and under $50 and belonging to this exact customer. Similarity narrows things down by meaning. The filter narrows them by hard facts. Put together, they power product search that actually respects your live catalog and per-user features that never leak one account's private data into someone else's results. That combination, meaning plus hard filters, is exactly what turns vector search from a neat trick into something a real business can safely run. You don't always need a brand new database for any of this. If you're already running Postgres, and half the world is, there's an extension that bolts a vector column and nearest neighbor search directly onto the database you already trust. It's shown here on screen, and it has become wildly popular for exactly one reason. No new system to run, no data to sync, no second bill to pay. Your vector's live right next to your users and your orders, and a single query can filter by an ordinary column and rank by vector similarity at the same time. For a huge number of apps, that genuinely is all you'll ever need. Start with what you already have in production before you go reaching for something specialized. When you outgrow that, a whole landscape of dedicated tools is waiting for you. Some are purpose-built vector databases like Pinecone and Weaviate, designed from the ground up to do nothing but store vectors and search them at enormous scale. Others are systems you might already be running that simply added vector search as a feature. Redis can do it now, and Elasticsearch can do it, sitting right beside the keyword search it's already famous for. The logos on your screen are the ones you'll bump into most often. They differ in the details, how they build the index, how they scale across machines, how much they cost, but every single one is solving the exact same problem. Store a mountain of vectors and return the nearest ones fast. Learn the concept once, and switching between them is mostly a matter of reading a different set of docs. The concept is the real moat here, not any single vendor's logo. Now for the use case that put vector databases on every roadmap: giving an AI model a memory. A language model only knows what it was trained on, and it cannot see your private documents. So here's the trick. Take all your content, help articles, past tickets, internal wikis, and embed it into vectors once up front. Store those vectors in a vector database. When a user asks a question, embed the question too, and use nearest neighbor search to pull the handful of chunks most relevant to it. Then hand those chunks to the model as extra context. and let it write the answer. The model isn't truly remembering anything. You are retrieving the right pages at the right moment and feeding them in just in time. That pattern, retrieval followed by generation, is how most modern AI assistants answer from private, up-to-date knowledge. Update a document, re-embed just that one, and the assistant instantly knows the new version, no retraining, no waiting. And the vector database is the retrieval engine humming underneath the whole thing. A few things will bite you if nobody warns you first. 1. Your query vector and your stored vectors have to come from the exact same embedding model. Mix two different models and you're measuring distance across two different maps. The results dissolve into nonsense. 2. Approximate search has knobs. The defaults are fine to start with, but at scale you will end up tuning the index for the specific balance of speed, accuracy, and memory your app actually needs. 3. The index usually lives in memory, and memory costs money. A million high-dimensional vectors is real gigabytes of RAM, so at serious scale, cost and hardware become part of the design, not an afterthought you bolt on later. None of these are deal breakers. They are simply the difference between a prototype that runs on your laptop and a system that holds up in production. So let's tie it together in 3 lines. 1. A vector database stores your embeddings and, far more importantly, indexes them. 2. That index turns finding the nearest vectors from a slow scan of everything into a near-instant jump to the right neighborhood, approximate, but fast enough and accurate enough to feel like magic. 3. Layer metadata filters on top, and you've got the engine behind semantic search, recommendations, and AI that answers from your own documents. Embeddings gave you the map. The vector database is how you actually search it at speed. If this made vector databases finally click, subscribe. This is a series, and every piece builds directly on the last. You now understand embeddings and the database that searches through them. Next in the series, we go one level up and put the whole thing together. Retrieval Augmented Generation, the complete pattern behind AI that answers from your own data. Give the video a like if it helped you, and I'll see you in the next one.